Welcome back. We're going to continue with our study of the Reynolds transport theorem. What I'm going to do first in this segment is show very quickly how the Reynolds transport theorem works when this field that we're working with is a vector field. Okay, because this is something we alluded to at the end of the previous segment when we said that psi could be, for instance, a momentum per unit mass, right? And momentum is a vector. Okay, so again, the title is going to look the same here. Okay, Reynolds transport theorem continued further. Okay. Okay, so let me put it down. What we're trying to do is compute d dt integral over omega t of a quantity which is psi x comma t d little v. And what we are seeing is that it can always be written as an integral over omega t of this term, the proper partial time derivative of psi, plus the divergence of psi v, okay, where v is the spatial velocity. Okay, so we've seen how this works out, of course, when in the case of psi being a scalar. But now let's suppose that suppose we do the following. Okay, we replace psi, which is a scalar, with u, which is now a vector. Okay? But then u again is a spatial vector field, right? So we're talking of u being written as u parameterized by the spatial position and time. How does this work out now? Okay? So the Reynolds transport theorem then takes on the following form. Okay? So the Reynolds transport theorem, RTT for short. Okay? It takes on the following form. It is that we want to compute d dt of integral over omega t of u parameterized by spatial position and time d little v. We can go through the steps just as we did before when we were deriving the Reynolds transport theorem for the case of psi being a scalar. The steps are exactly the same. What we end up with is the following. We get integral over omega t. Once again, we will have the pure partial time derivative of u, plus we will have the divergence of u tensor v. Okay. All of this dv. Okay. To gain just a little more insight into this result, it's useful, as it's always been, to go into coordinate notation. Okay. So let's just see why this. Let's see if going to coordinate notation gives us any insight into why this result should work out. First of all, it may be obvious to you already that has to be the way things work out. Of course, you could get to it by deriving the whole thing, but let's just not go that far, but try to see if coordinate notation can give us further insight. Okay, so in coordinate notation, here's what we would be trying to do. Okay, in coordinate notation, we would be trying to calculate d dt of integral over omega t of each component of u. right, where each component of u, right, we're trying to compute this, trying to compute the time variation of that integral for each component of u, right? But now if we observe that each component of u is essentially a scalar function, right? So Reynolds transport theorem as derived originally for scalar functions can be applied here. It's completely standard. There's nothing new that we're going to see in this particular step, okay? This then becomes integral over omega sub t. We would get the partial time derivative of ui plus the divergence of ui times v, but where v is now the direct notation representation of the vector v, right? Sorry, ui is being multiplied by the direct notation representation of the vector v, right? All of this d little v, okay? But now you observe that what we have here is essentially a vector of the form ui v1 ui v2 and ui v3. Okay? Right? Now, when we go to I equals 1, 2, 3, right? We're in coordinate notation, right? And that's why we have an index I. When we let that index I run over 1, 2, 3, what we will see is that instead of that vector that I've just written there, we will actually have 3 column vectors, right? Okay, but then those 3 column vectors will essentially represent the dyadic product of U tensor V, right? For I equals 1, 2, 3, right? The term that we had, integral over omega t, what we get is derivative with respect to time of, now explicitly u1, u2, u3, right? Essentially, on the previous slide, we wrote out an equation for a particular value of the index I, right? As I runs over 1, 2, 3, we essentially have three of those types of terms, right? So we get this plus divergence of, now likewise we get u1, u2, u3 tensor v1, v2, v3. Okay, right? It's the divergence of this entire object. Okay, this, now we'll go backwards, writing the right hand side and then the left hand side, is essentially integral over omega t ddt integral over omega t of u1, u2, u3 d little v. Okay, that's why things work out. Okay, so this is how this is the result that we see. I'll go back to the previous slide here. This result that we see is what we get when u, instead of being a scalar as before, is a vector. Okay, so that's the generalization of the Reynolds transport theorem to vectors. All right. Okay, to finish up this segment and our formal treatment of Reynolds transport theorem, I'm going to try and provide a little more insight into what the Reynolds transport theorem is trying to do here. Okay, let's look at this as physical insight to the Reynolds transport theorem. And for this purpose, I'm going to use psi as a scalar, but what we've seen that the generalization to vectors is completely straightforward. In fact, you can just imagine, you can pretty much pretend that whatever holds for psi simply holds for every component of a vector field, right? And you don't have to pretend that's actually what is actually happening. Okay, so I'm going to work with scalars, psi. Okay, so once again, we're doing this, right? We're trying to figure out this. Right, and now we figured it out mathematically, and what I want to try and do here is to give ourselves a little more physical insight into what's happening. Okay, remember psi here is some spatial field. Psi of x comma t is a spatial and time varying field. Right? Right? It's varying spatially and with respect to time. So I have space in front of me, right? So you have some field psi that's varying over here. It's varying from point to point. It's also and at each point it could also be varying with respect to time. Okay? And now we're trying to compute this integral that we've written down here. We have computed that integral over some region in space, right? Over some configuration in space. This configuration is our omega t. Okay, and we want to know how that integral we just computed is varying, but with the further twist that this configuration, this region in space is itself changing with respect to time. Okay, essentially, all right, so that's what we want to figure out. What we're finding then is that the transport theorem tells us that this can be simply written as an integral over the same volume, right? That volume at that instant in time, right? Omega sub t. It's the integral over that volume of simply the time rate of change of psi, right? Simply how is psi changing at every point, right? With respect to time, right? So we have this region in space, okay? You fix time t, right? So we have this region in space at that particular instant in time. The first term in that integral is simply how is psi changing at every point in this domain, right? That's the first term, the partial time derivative of psi. But there is a second term, right? And that second term is a divergence term. Okay? What I want to do is what we need to do is gain more insight into what that divergence term is doing. And in order to do that, we are going to invoke one of the most famous theorems in vector calculus. It's called the Gauss divergence theorem. Okay? So, the Gauss divergence theorem right? It can be applied to vectors and tensors. Here we're going to apply it to the vector that's involved in psi times v. Okay? So the Gauss divergence theorem tells us that the integral over some volume of the divergence of our vector psi v d little v is integral over the boundary of that domain of psi v dotted with the unit outward normal little n to that domain integrated over the area of that domain, right, over the area element. Okay? So the picture, if you recall, is this is omega sub t, right? Inside here we have a vector field, psi v, okay? And what it is telling us is that the divergence of this quantity is integrated over the volume, omega t, right, is simply an integral over now the surface, right? Okay. It's an integral over the surface of the vector dotted with that normal, okay? And we may look at that as being an area element d little a, okay? All right. And we you know, we've seen this sort of thing before, right? We know that when we compute the divergence of a vector over a domain, the divergence really has this notion of, you know, you take a little pillbox here, and the divergence operator tells you what is the net outflow over that little pillbox, right? So it tells us that, okay, if you have the vector coming in here and leaving from other surfaces, okay, the divergence of psi v is the net outflow over that little pillbox, right? So this is the net outflow over every volume element dv, where this is my volume element dv, right? The little pillbox there, okay? That's what the divergence is. So when you integrate the divergence over the volume, you're getting sort of the net outflow over the volume. But then Gauss's insight was to say that, well, I could just integrate over my surface and calculate the net outflow over my surface. And that's what we get when we compute here. We compute psi v dot n, right? We know from the physics of the from the interpretation of the dot product that dot product is the vector psi v oriented along our normal, okay? So essentially what we get is the following. When we apply the Gauss divergence theorem, what we're seeing is that when we apply this to the Reynolds transport theorem, what we're seeing is that d dt of integral over omega t psi d little v, okay, the first step here comes to us from the Reynolds transport theorem, which says that, well, just account for how psi is changing at every point in the domain plus this divergence term, right? This is what Reynolds tells us, right? But then along comes Gauss, and Gauss says, yeah, you could write that as that first partial time derivative, and Gauss didn't care too much about this term. But then he said that second term I like, and in fact that second term you should rewrite in this form. Okay? All right? So what this is saying is that over my volume, right, I have this volume, and this is my configuration in time, right? My configuration over space at time t. You want to know what the total rate of change of psi is if you've integrated it over this volume, with the additional problem that this volume is not staying fixed in time. Okay, so the combination of Reynolds and Gauss tells us that, well, it's easy. The first term is just you fix that volume, you freeze that volume in time, and look at how psi is changing at every point in that volume. Integrate that. Okay, and then along comes Gauss. So now this is where our body becomes useful again. So we have this volume in space. I've put the body back to occupying that configuration omega t just for us to be able to see that configuration. So the first term says computes the rate of change of psi at every point in that domain, integrated over the volume. The second term is to account for how this body sweeping through space, okay, the body sweeping through space is incorporating some of the field along its boundaries, right? At points where the velocity is sort of oriented outward, right? The velocity of the body at certain points on the surface is oriented outward. At those points, it is sweeping in more of that field psi, okay? And that is what we see is happening right here. At points where v dot n is positive, like here, let me use my approved arrow for this, right? At points such as this, right? If the body is tumbling through space in this direction, this is v dot n. Okay, when it's tumbling through space in this direction, it is sweeping in points of in space and thereby incorporating that field psi at a rate which is given to us by v dot n. Okay, right? Or at a volume rate which is v dot n dA. At the same time, at a point such as here, where the velocity is directed inward, it is losing that field because it's you know that field in space is sort of leaving the body, right, as the body is going out. Again, our term v dot n acts to tell us that where v dot n is positive implies that psi x comma t is sort of entering the body. Okay, and at points where v dot n is negative, it implies that there you have this quantity psi is leaving omega sub t. Okay, so it's as if this is what we have at this time. Let me try and draw this here. So this is the body, so this is the configuration omega t at say time t1. Okay, and what you're seeing is the field that you have. Now at time t2, let me suppose that the body changes to something like this. Okay, at points such as here, where v dot n is less than 0, we're losing some of that field. At points such as this, where v dot n is greater than 0, we're gaining more of the field psi. Okay, so this is omega t, and this is omega, sorry, that was omega t1, and that's omega t2. Okay, it is this effect that's included by doing this integral. Okay, that integral is negative in places like this, and it is positive in places like this. Okay. All right. So that's a physical interpretation of what the Reynolds transport theorem is doing. It tells us how we can account for all of the time variation of a spatial field defined over a region in space, where that region in space coincides with the position of the body at that instant in time. Okay? This may have been, hopefully this hasn't seemed like too abstract a series of segments, but what we're going to see in the segments to come is that this will be used repeatedly to derive further balance laws. All right, we'll stop here.